and good afternoon to all of you, and welcome to our third Smart Grid Educational Series seminar. This is a monthly event, and IBM has been very kind to offer these facilities to us here in Foster City, California, to carry out these seminars every month. But because the topics are of interest to people all over the country and ultimately all over the world, I have started sharing these seminars in a concurrent webinar that goes out to some 1,600 people in 10 countries. And we are seeing some of those people today, this afternoon, this evening, this night, tomorrow morning, depending on where they're calling in from, that are listening in. The purpose of the Smart Grid Educational Series seminar, in addition to the monthly webinar that I host on the second Monday of every month, these seminars are occurring on the fourth Monday of every month. And the primary purpose of this is to have some human interaction, have some networking opportunities here in the Bay Area for people who are in the field of smart grid, clean tech, energy efficiency, and IT as it pertains to the energy sector. We're trying to get people to make a habit of coming to these events on a monthly basis, have some subject matter expert or a group of experts talk on a subject in this area and pull all of you into an interactive discussion. And with the folks on the webinar, the idea is that you will share your perspectives through these remote connections and also feel like you're part of the community. And if you have opportunities to interact with some of the people who are presenting or people here in the audience, you can, through email, let me know, or by posting comments here. So I've created essentially a virtual networking environment so that on a regular basis you know where to come. The Highway 92 and Highway 101 are well-established freeways in Bay Area. Everyone knows it's close to SFO. So I'm taking away what I call the element of plausible deniability from you by saying, I didn't know something like this happened. So that's the reason why we're doing it. And once again, Chris Heckert and Naina, his boss, here in Foster City, giving us this facility, promoting these events for us. It's a really kind gesture. So thank you, Chris.
You're welcome.
All right. So without any further delays, what I'd like to do is introduce Frances Cleveland. Frances is an independent consultant. She runs an organization called Xanthus Consulting International. Frances and I have worked for 3 years now, almost?
Probably. Or
through the NIST work, and then worked as a subcontractor on several EPRI projects when I was working there. And then in the NESCOR project, Frances made significant contribution and continues to make significant contributions. Now, the interesting thing about Frances is that she's very multifaceted. She has an understanding of power systems in multiple ways. And she's not one of those what I call armchair anthropologists. She actually rolls up her sleeve and contributes in the working groups, in the domain expert working groups of NIST. She's been very active in IEC. She chairs a working group for cybersecurity under TC57. So Frances doesn't need much of an introduction for people who are in the business. But since there are a lot of people who are just entering the business, I have to say that if distributed energy resources was like floods, you're going to hear a seminar on floods by NOAA. And I want you to appreciate that, because it's very rare that you get people to speak firsthand about things. I mean, literally, the objects that she's going to talk about that are being developed in distributed energy resources that will eventually become part of 61850-7-420. Those objects, their attributes, are actually being defined by Frances and other people like her. So this is like about as firsthand as it comes. And when she talks about power system issues, like from a stability perspective and from an interoperability perspective, understand that she has consulted with enough power utilities to know what she's talking about. So I'm really, really privileged at this point to introduce Frances Cleveland, who's going to speak, I believe, for about 45 minutes. And she will entertain questions throughout her talk, and then there will be a formal Q&A period. Just the logistics, we have a break, a networking break that will follow this presentation, and then we're going to bring up Ed Cazalet from TMIX, or the Cazalet Group, depending on how you want him to be viewed. And then we have Craig Lewis from the Clean Coalition, who's also going to join the panel. Frances will be the third panelist, and I will moderate that panel discussion on DER. So with that, Frances Cleveland.
That's what I gather. Okay, good afternoon, everybody. This is a gorgeous day here in California. So what I'd like to start off with is, first of all, just getting some understanding of what at least the audience here knows about distributed energy resources. So first of all, does everyone know what DER stands for?
Yes.
Okay, boy, that's great. Okay, how many people have actually worked with DER systems in any way, either on paper or implementing them or designing them? So don't be shy. I'm trying to get a sense of, what you're involved in. Okay. How many people have dealt with communications with respect to DER systems? Okay, a few of you. All right. Now, just a little bit, how many people have dealt with cybersecurity for DER systems? Oh, one hand at least. A couple of hands here. Okay. So, not that I'm going to get into any gory details on the cybersecurity, but it helps to have an understanding of where we're at. Now, Erfan, do I need to make this bigger, or or is this the way it's supposed to be? I'm not sure of your.
Lower left corner. Keeping the comments on the side so we can see, but you can go full screen.
Okay, I just think it's easier for people. I have a few eye charts, so I try to avoid them. Okay.
And the arrows, when you scroll up and you go up on top of the screen, you will see. Yes.
Okay. Well, I'll just use the arrows. Okay. I'm going to discuss, what I'm going to try and do is provide sort of an overview of where the issues are with respect to DER and the communications, the functions, and then the communications that enable those functions. So one of the things that I like to start off with is for people to understand exactly how broad an area this is in the smart grid. It's no longer just part of the utility world. It's not just part of customer, washing machine world. It's not just markets. It's not even ISO, TSOs, RTOs. It really covers a broad area. And then I'll get into some architectures and some of the benefits of DER, and then, of course, the challenges of DER. And then trying to meld the two together or get them to work together where there's a win-win between the capabilities, the benefits of DER, and matching them with some of the challenges. That, of course, involves communications, and I will get a little bit, I won't go too deeply because it can be mind-boggling, to get into the 61850 communication models for DER. So I'm going to try and stay at the conceptual level so that people can understand it. I'm not going to get down to all of the little objects and stuff like that. Oh, that's right, I have to do that. So the DER architectures and the benefits. So I'm going to start small. I'm starting now with the actual DER systems. And you'll see that there's sort of a green bar that the controllers and sort of computer type things are connected to at the top. And then there's the red bar at the bottom, which is the power system. DERs are cyber physical systems. And this is quite important to understand because a lot of people who take a look at the smart grid just say, oh, I'm just going to have computers do things and I'll have them crank out something and send that information and it's a done deal, without realizing that there are physical, electrical consequences to these things. And so you really have to remember that these are physical, electrical animals that you have to deal with. So there's this cross where you have the controllers and such that are managing the physical devices, and then there's the impact on the grid. So as you can see, DER devices consist obviously of generators like photovoltaic systems. They include storage devices like batteries. They also include electric vehicles where these can be used to actually act as something more than a load. You also can include loads in the sort of overall picture, and that's sort of a debate is exactly how much in the DER world you want to cover loads. But, you know, generation is offsetting loads, so it's sort of a balance there. So in this is sort of a DER site. It could be at a customer. Could be at a utility like a substation, and there's typically a meter like the one off to the left that connects into the electric grid. Now the benefits to customers are that there are a lot of cost savings for customers. You can do net metering, feed-in tariffs, other types of tariffs to reduce the overall electricity costs. For instance, I put a PV system on my roof maybe 4 years ago, almost 5 years ago. I have not paid a penny to the electric company since, except for the $5 a month, literally the connection to the grid. It has significantly reduced my costs there. Now, obviously, there were capital costs to install it, and that's the whole cost-benefit issue. But it really does pay off in the long run. DERs, although right now are not often looked upon as being part of a demand response program, most of the time people are just looking at loads. Nonetheless, they can be managed and manipulated just as much as loads, if not more. There can also be direct marketing participation and pricing tariffs. Then there are other things, emergency backups. So you can have the DER system. Unfortunately, my PV system doesn't work that way, but you could have them for backup. In fact, one of the uses of electric vehicles, one of the first sort of non-car uses of electric vehicles is the idea that you can back up your house. And that's very attractive to a lot of people. I live up in the woods, up in the Santa Cruz Mountains. And believe me, the power goes out often. So we have a little diesel generator, but I'd prefer to have an electric car doing it. So now I'm going to sort of build this architecture, just to let you know. There are 5 slides that have these diagrams of the architectures. So now I'm building it up. So you still see the green area, that's the DER systems themselves. Now they can be managed by some kind of DER energy management system. That could be just within your own residence. You have a smart box that sort of manages your device for you. Or more likely, especially in the beginning, it'll be a commercial or industrial customer, like a shopping center or a university campus, or even a cogen plant at an industrial site. It can be the utility-owned site, again, at a substation or a power plant. So here, we've added the next layer. It's very much a hierarchy. And that's one of the things I want to get across, is how important this hierarchy is in trying to manage DER systems. Remember, there already are millions, and there are going to be even more millions, and they're all going to be now interconnected to the same feeders, the same electrical systems. So how are you going to manage it? And this is where we start seeing this hierarchy. So this is an important aspect that sort of locally, if you can call a campus a local control, locally you will have some kind of energy management system that will manage this green DER set of systems. So the benefits there are that you can optimize the energy usage through combined generation, storage, and load management. So now we're sort of at the next level up, where we can use the energy management system to assess the energy needs over specific time frames, not just real time, and schedule energy generation and energy usage, including, charging up batteries, as well as when you want to discharge the batteries. You can also use some of the byproducts from, particularly this is industrial processes, like combined heat and power. So there's a lot of other areas that you can begin to get involved in, including carbon trading, which is finally beginning to bubble up, where if you have a DER management system, you can begin to participate at a broader level. My little PV system has no particular smarts. It just, when the sun shines, it generates electricity, and at night it turns itself off. That's it. Now, if I had a DER management system added to that with a little bit of communications, I could do a lot more manipulation, making sure what I could do, particularly if I had some storage. PV systems kind of go with the sun, but if you had storage, then you could sort of balance them off each other. So, third layer. Now that you've got the DER systems in the green, and it sort of shows blue there, the DER energy management system, now those can be interacted with the retail energy providers and the utilities, who are now telling you what they would prefer you to do, either through pricing, or there could be a tariff where you're told you're going to do this or do that. Or, you've got some kind of agreement with them that they're going to manage your systems. So this is the third level. I'll get into a little more detail about what they might be telling you to do a little bit later when I get into the functions. So, again, the benefits here are now that there's sort of this interaction with utilities, and that's even the energy service providers, the reps, are doing it based on what the utility needs. So this is now combined or shared cost savings by both utilities and customers through net metering, the feed-in tariffs, and so forth. Certainly a demand response if it really begins to look at DER in addition to load. And so there's a lot of other things where now you're beginning to share what the benefits are. So fourth level, I've now expanded out that utility box that was up in the left-hand corner at the top, because here it gets even more difficult. The utility needs to know what to ask the DER systems to do, what to command them or request them to do, what price to set, when should it ask for what should it schedule. That is a very complex area. It's not as simple as when you have bulk generation, where you basically have a bunch of base load generators and you just, based on market conditions, you basically base load them, and then you have a few that work on AGC and you pump them up and down. Now all of a sudden we've got millions of tiny little things out there, all in different feeders, all with different constraints, different capabilities. It's complex. So there's, over on the right-hand side, there's a GIS system. That's where you can at least know physically where these devices are. You've got maybe something here, a distribution management system, so that the utility is running its distribution system, and then combine that with on the left-hand side, the DER management system, so it can combine that information. Then you've got additional boxes, outage management systems, and if you do the demand response system, actually there are going to be hundreds of these boxes. This is, much simpler view of it. But I think the main takeaway here is that the complexity for the utility is very high. It's unknown really how well they're going to be able to manage these millions of independently operating devices. And this is why you need to really have sort of this hierarchy. There's no way a utility can talk to 1 million devices and tell them precisely what to do. Bulk generation, they can do that. They've just got a few of them, they tell them what to do, and off they do it. With DER systems, you can't do that. So you have to have a different mechanism, a different way of managing this. But there are then great benefits. If the utilities can figure out how to do this, then there really are great benefits. Really increasing reliability, because now we have generation all over the place. And if you can manage it properly, you can provide spinning and operational reserves for local areas. You can support intentional islanding for campuses, housing developments, and other areas, so that you can at least provide reliability for them. You can decrease your own construction costs by not having to put in as many wires. If you've got generation supporting an area and you can count on it, that's another challenge for the distribution companies. You can defer your own construction. You don't need to put in bigger transformers or heavier duty wires or spread it out. You let the DER systems help you balance that. And then in addition to others, you can improve power quality. Now, power quality are things like voltage sags and swells, or voltages out of limits, also VAR support, including outages. Outages are also looked upon as power quality. If you can have a little microgrid, then you can avoid an outage. You might have a dip, but then the microgrid forms and you're not out of power. So there are a lot of real benefits to this, to DER systems. You can increase generation capacity and decrease load just by saying, okay, let's shift a little bit. Maybe turn on not the PV system so much, but let's say you do have some kind of fuel cell, and you say, okay, I'm going to turn this on, and so that I can then decrease my load, but simply by turning on my extra generation. So the net is decreased load. You can also have both real power plants, just a whole bunch of DERs, like, a field of photovoltaics or a field of wind turbines sitting there. Or you can have virtual ones where somebody has contracts with all sorts of disparate customers that they're going to run as a power plant and buy and sell into the market, but they're located all over the place. You know, somebody's house, a wind turbine in a farm somewhere, and they manage this. So this really will help handle this fact of millions of devices. And this will also, of course, help energy efficiency. You can now manage efficiency of the power system right there where the problem is. If you've got voltage that's a little too high, you can ask the DER systems to lower that voltage. If the voltage at the end of a line has dropped too much, you can use the DER systems to boost it up a bit. And you can do this on a much finer grain than you can with using cap banks and capacitor banks and other voltage regulator type devices. So this and VAR support and what's called low voltage ride-through, actually it's low-high voltage ride-through conditions, these are all things that these DER devices can provide. A tremendous benefit to the distribution utility companies. So my final picture of this sort of DER management architecture, you now see, of course, the green at the green rectangle at the bottom, the blue one with their DER management system, the utilities, all systems that are managing, trying to figure out what to do. But it also ties in to the transmission system so that you have, and the independent system operators and regional transmission operators who are trying to use the generation that you can get from, and the ancillary services that you can get from these DER devices that are connected through the distribution system. At the moment, they have no direct access to that. But they need these services. Transmission lines need VAR support. There's a whole bunch of things that particularly with the renewable energy, where the ISO is trying, for instance, Cal ISO, is trying to figure out, well, you know, if the sun stops shining in one area or, you know, a huge cloud comes over, all of a sudden it stops, the wind stops blowing, and all of a sudden we have to pump up other generation. They need to know this. So they need to know a lot of information. A big effort that's going on now is weather forecasting. And this is micro weather forecasting, not just, you know, well, it's going to be, you know, 85 degrees here today, and, you know, it's sort of going to be slightly different in other places. No, it's micro climate that they're really interested in, because only that way can they predict with some reasonability of certainty that they will have this level of generation to work with. So this is an ever-expanding big system that has to be managed well. So again, as I was saying, the benefits to the DER for transmission and ISO RTO operations in aggregate, not individually, but in aggregate, supporting the energy balancing operations, the balancing of generation against load, which is their purview. Providing frequency support. You wouldn't think that a tiny little DER device, you know, and here's the whole Western interconnect or the Eastern interconnect is all connected at one frequency. You wouldn't think that a single little DER device could do something. Well, it can't, but a whole bunch of them together can. And so this is where they're beginning to look again at the big picture to show how this will work at that level. Providing things like the low-high voltage ride-through, so you don't disconnect. You know, right now most DER systems are required to disconnect from the grid if there's some kind of anomaly going on, some kind of voltage fluctuation going on. And if it's a true outage, if, you know, the voltage drops to zero because there's really, you know, a tree crashed through a line, fine, okay, you really want to disconnect. But if it's just a jiggling of the voltage for some reason, you don't want them all to disconnect, because what will happen is then indeed you will get an outage. So you don't want to disconnect if it's just sort of a fluctuation. So providing the low-high voltage ride-through is particularly important. And then some of these ancillary services, voltage, VAR, support, it's called spinning reserve, operational reserve, and some of these other things that NERC really needs. Can even provide black start capabilities. If you start small, you can start up your system and then grow it larger. So, and of course, energy efficiency, because I think that also is part of this whole thing. And just to be a little green here, the benefits of DER for society, at least for the renewable energy. I mean, we don't really need to preach here in California on this, but it will reduce the carbon and pollution problems. Of course, we're having an issue now, renewable against, that cheap natural gas that's now starting to flow. But anyway, so we need to meet the mandated renewable portfolios and providing green power for socially conscious people. Up in Marin, they're doing a lot of that. So I think it's really an important aspect to look at it, not just from the economics of customers and utilities, but also from society in general. Okay, how do you manage this? What are the challenges? Now, I've sort of covered some of them already. This is the SGIP, the Smart Grid Interoperability Panel, that I suspect most of you have seen at least something similar to this, where there are the different domains. Why don't you raise your hand if you have not seen something like this with the 7 domains? Okay, everybody is up to date on that. So my point here is that the
Can you minimize the screen and just have a look at the chat window to make sure the folks on the webinar are all with us, so that there is no issues? Almost as last comment from screen.
Let's see, in this case, energy generated by the PV is fed back to the grid or used only within the home. If it is fed back to the grid, the same electric meter is going to manage the energy transferred. And the answer there is you have a net meter. I have a net meter. It meters essentially both directions, subtracting one from the other. But it also meters on a 15-minute basis, so that what you have is during the off-peak hours, you get charged or charge a certain rate, and on peak, you get charged or charge a different rate. So during the hot afternoons, like right now, my PV system's making me a lot of money. Only I wish PG&E would give it to me, but they don't. So yes, indeed, the net metering works that way. Well, I think the rest of them were I can hear you.
Oh, I see.
So that's why I was sort of being...
Let the audience know on the webinar, Francis, that we will announce the questions. I think that's...
Yeah, yes, yeah. So, yeah, I think there was a question here. Please repeat the questions if you're able, thanks. So that was, the question was what I was saying about if it's fed back to the grid, the same electric meter is going to manage the energy. Well, it's going to meter the energy. It doesn't manage it, but it meters it. Okay. So
maybe the question is, maybe Francis, the point is that we may need more. I mean, we need more management, not just metering.
Absolutely, yeah, and that's where I forget if you came in after my.
Sorry,
yeah, I know you came in. You have a sick son,
yes.
So. All right. So some of the challenges I've noted already, particularly for utilities, just knowing what to do. So what I have here is, a diagram that basically says if you want to manage the system from a utilities perspective, you have a whole bunch of applications and assessments and other things that you need to do. I'm not going to get into all of these applications, but some of them are like volt-var optimization or contingency analysis. Let's make sure that the system is reasonably stable and that if something goes wrong, we have something that backs it up and we can recover without having an outage. You have fault location, isolation, and restoration function. So that, and this is all somewhat standard distribution automation, but now you have the DERs to add to it. As you can see, there's just a tiny little DER up here in this corner, but it has a major impact on all of these functions because all of a sudden it's not just power flowing from the transmission system down and out to a customer. Now it's going all over the place. And particularly as we get into having some of these ancillary services provided by DER systems, it's going to become increasingly complex. So the sheer complexity of the big machine, I mean, we've always talked about the electric power system as the most complex machine ever invented by man. The smart grid is about to become even more complex. And so it is an absolute challenge. I don't think we can minimize that challenge, minimize talking about it and recognizing it. I've had DER installers who would just love to install a new DER system somewhere saying, why can't the utilities just let me do it? It's so obvious. All I have to do is connect it into their wires. End of story. And I have to say, well, did you think about what might happen if this happens or if that happens or what they need to do? Oh, gosh, never thought of that. So this is something that is really important to understand, that it is not simple. That said, the benefits, as I've been saying, are tremendous. So it is a question of how do we move forward without bringing the power system down or, causing terrible outages and other problems, and yet still bringing in all of these DER systems that are ultimately so beneficial. So I did mention some of these functions. These are just sort of a few additional ones. Situational awareness is one of the things that is absolutely needed and yet is terribly difficult to get. And by situational awareness, it's sort of a catchword, and it can mean a lot of things to different people. It basically means knowing what the power system is doing. What's out there? What can it do? Not just what it's doing at the moment, but what can it do 10 seconds from now, 2 hours from now? So there's a lot of monitoring that needs to go on. But the monitoring can't be, from every single DER device. That's just not feasible. So how do you do this situational awareness, getting in the information that you need so that you can make the decisions that you need to make? So again, these are really some of the challenges here that need to be met. I mentioned the volt-var, actually it's volt-var watt optimization, and this is one of the drivers of some of the functions that have been developed recently. I will get a little bit more into that. But in addition, there's the whole issue of contingencies. And right now, the transmission systems do contingency analysis because they can say, here's the transmission line, and there's a limited number of them, and we know where the generators are, and we know from CAL-ISO and the other ISOs, which generators are doing what. That's not going to be the same thing with the distribution DER. First of all, there's not really any contingency analysis programs in the distribution system. So this is going to be another huge challenge. And then how do you mix it and work together with load management? This is going to be another thing. When do you want to have more generation and less load? Or, how do you want to work that mix? this just gets into, I think I will just go through this a little bit more quickly here. These are just some of the issues that you also have to look at. If you're grid connected, you can be just within a residence, or you can be within a building, a power plant, substation, campus. You know, it's all over the place. It's not just in a power plant, which is the current situation. And now we also have microgrids. And I'm talking here about truly electrically disconnected microgrids. Some of them are permanent, and that's fine, but some of them have to be managed as you go in and out of them for whatever reasons, as backup or as autonomous decentralized control, pre-planned microgrids, emergency microgrids. There's a whole bunch of things where now you actually actively want to disconnect part of the grid. That's never been done before except in total emergencies when you want to black out only part of your territory. And of course, the DER systems are also not just managed by utilities. That's another whole new aspect. They're managed by private customers. I manage my own DER system. I look at it occasionally and smile. Well, that's it. But others will be managed by retail energy providers who are going to be out there wanting to make money off of it legitimately, managing it for a bunch of different customers. Utilities will have direct control over some of them, but they're more likely going to be sort of cooperative efforts where it's going to be a win-win situation. Demand response will probably get into the mix. As I mentioned before, microgrids as well. Now, these are virtual ones where we're really talking about pricing, where you say, well, I'll keep down the total load or the total demand, let's say, between 2 and 4 p.m. For a price break. And that, then within the virtual microgrid, you decide how you want to do it. You want to discharge some batteries or something. And then you can have these virtual power plants that I mentioned before where you can aggregate generation from all over the place and storage and manage it as a whole. So the question is, how do you match these things? The benefits, the needs, and the challenges. And although it's a long, hard process, I say there is sort of this win-win where everybody can benefit, but it needs well-defined functions, it needs well-defined communications, and well-defined standards to go along with it. So just a little bit of understanding of how these functions that have been developed work is the fact that you're not going to be looking, these functions work not just at a total customer site, behind the meter they can do anything they want, because now we've got DER systems all through, like say university campus. The university may be billed just at their metering point, but behind the scenes there's a lot of management, and these functions that I'm going to be talking about need to do it behind the scene as well as in front of the meter. So what we've done is we've called it an electrical connection point. I won't get into more detail than that. There's more detail can be provided if you're interested. And so there are multiple ECPs, say, behind the point of common coupling, which is typically the metering point with the utility. So the idea is that DER management is not only at the PCC, which was what was originally expected in the original 1547, which is the interconnection standard, but it's also at these ECPs. I'm going to speed up just a little bit here, but I think what I want to make clear here is, why are inverters so important? Now, some DER devices, like a diesel generator, does not have an inverter. It actually may have a double inverter, but let's stick for the moment for a simple concept. Anything that's already rotating could have an inverter that sends it to DC and then sends it back to AC at the frequency that you want, 60 cycles. But most generators that are, say, like photovoltaic systems or wind turbines or fuel cells actually generate DC power, and then it gets inverted into AC. This happens to be a very, very convenient place to play around with the electricity so that you can make it do things that you never thought you could do before. So this is what's really important. Inverters are really software driven. You can tell an inverter to do an awful lot of things that you didn't think it could do. So the point here is that now, instead of being sort of a dumb machine that just does what its hardware does, you can program the inverter to make it do a lot of things. For instance, it can change voltage levels, it can change VAR output, it can literally figure out, have algorithms as to exactly what level it's going to go, where it's going to be. So this is really a critical point. Given that, some of the functions for DERs are fairly straightforward. You want to turn them on, you want to turn them off, that's fine. You might want to limit their maximum output. If for some reason there's too much generation on this feeder and you're overloading, say, a network, a power system network behind it, that sometimes is a problem. You want to limit the output. In fact, that's becoming a problem in Europe right now. They have all of these wind turbines, which are terrific, but the wind blows at night a lot of the time, as well as during the day, but it blows even more at night, and there's no power. They can't eat up all of that power, so they actually have to back off of the power. So you can limit the maximum output. Now, great if we had storage that generate all the storage. You can charge up all of the EV batteries and so forth. But anyway, that's one of the functions. And obviously, you want to do some status monitoring and event logs. You want to know what's happening. That's part of that situational awareness. But the interesting ones are these modes. And the modes basically say, okay, we're going to assume that DER systems are quite intelligent. And within the controller part, remember the green part in the green box where you have the controllers, they can say, we want to do volt-VAR control, and we're going to tell you precisely how we're going to do it. We can do frequency watt control. We can do volt-watt control. We can do low-high voltage ride-through. Temperature control. So if the temperature gets too hot, you can change the VARs. So these are all really interesting software-driven functions, and that's what makes the difference. You can also have schedules. You can say, I'm going to schedule it to do this volt-VAR mode at between noon and 6 p.m., and this other volt-VAR mode, or maybe no volt-VAR mode, after 6 p.m. until midnight, things like that. So this is where we're moving with respect to these functions. So let's take a look at these fancy inverters. They're really 4-quadrant. That means you can have them move. This is with the VARs. You can have them leading or lagging VARs, whether they're charging or discharging. That's basically the 4 quadrants. They actually now are using different terms, but that's, I'll leave it to the detailed inverter folks as to what the terms are. But that's basically, you can run in any of the 4 quadrants. If you have a generator and storage, particularly a storage device actually works in all 4 quadrants. A pure generator can only work, obviously, in the generator quadrant. So this is what the software can do. It can change those angles and set you in any one of the 4 quadrants if you physically can do that. So let's take a look at some of the modes. these are functions that have now been defined through both an EPRI project and through the IEC work, where we have arrays of volt var settings, which basically the array, if you see down at the bottom, you can see that there is a graph down there, and it's VARs generated on the vertical, and it's system voltage on the horizontal. And so you can literally create an array that matches this function here, so that if the system voltage gets too high, you change the VARs that are generated, or actually you change them, you decrease them, and vice versa. So that's, and again, because it's software driven, you can just put this right into a little controller. So then you have to add additional things like ramp rates, a time window within which you randomly make this change. What we don't want is a million of these DER devices to suddenly switch, just like that. You know, then we're really going to have problems with the power system. So we give them a time window. The time window could be 1 minute, could be 10 minutes, it could be 2 hours, you know, depending upon what you want to do. And then randomly within that time, you change the DER to whatever it's being asked to do. Now, obviously, if you want to shut it off, that's a 0 time window, you know, shut off right now. The timeout, you add a timeout period in case of loss of communications, and you can add hysteresis. So that here it shows a little more clearly. The bottom one shows the hysteresis, where if you're going in one direction, you have one curve. If you're returning, you have a different curve. And that can get quite complex, but it really adds some true benefits. Schedules, again, obvious, but the point is that in these functions that we've defined, you can have multiple schedules, and some preempt other schedules and last for short periods of time, and then let's say the original schedule takes effect again, and so forth. So there's a lot of capabilities in these schedules that are being defined. There can also be pricing signals. To some degree, we're leaving that open to the demand response folks once they get around to it, but that's what we're allowing anyway.
Francis?
Yeah.
Can you check the comments again? There's some audio issue that Nick was having.
Okay, it says, one person says, I have lost audio, and then he says, just came back, lost it for a few minutes.
Yeah, so that must be because of his own individual internet. Okay, very good.
Okay, well, as usual, as all speakers do, we push the time limit, so I'll try and get going a little bit here. I keep talking about these functions. These functions were defined partly as an effort by EPRI, and some about 100+ people were involved. Let me see if I have that. Oh, this is a nice little diagram, but it doesn't really add very much, so I will jump to the next one. Well, that doesn't add. Well, I'll get into this. But anyway, it was an EPRI project. We also then took it to the SGIP. We also took it to the IEC for the 61850 effort there. And we have now developed those functions and converted, defined them as object models in 61850. So it was also driven by the Europeans, because these kinds of functions, when they heard that we were starting to work on these kind of functions, they said, we've just been mandated to put this stuff into all PV systems in the next 2 years, and that was about a year and a half ago. So they're very busy putting these functions into their systems right now. Huge effort in Germany, another huge effort in Italy, and so forth. So, these efforts are going to pay off, I think, pretty quickly. So one of the things that I wanted to do was kind of set the stage here, which is that we can have the functions defined, but what are we going to define them in? And we selected 61850 because it is a standard that is focused on field equipment, originally substation automation, but has now really expanded to include any kind of field equipment. And so this is really important because if you're dealing with real equipment, if you have a cyber physical / electrical system, you have to take that real world stuff into account. It's not just computer databases and applications. So it was very important to find a protocol that allowed this kind of field interaction with equipment and knowing what the equipment was really going to do on the power system. So we did do that. We did that at the abstract level. So we've got basically a paper document. It is being turned into electronic form at this point, but we have basically a paper document that says this is how the functions work, and these are the communication objects that are going to be exchanged. But then we needed to convert those, this paper abstract stuff into bits and bytes that literally go over a wire or wireless or whatever. And that's where we've also mapped it to DNP3. We've mapped it somewhat to the smart energy profile, but that's, of course, not quite here yet. There's also been mapping to Modbus and a few other things. So, and as well, it's also mapped to what's called the MMS, the Manufacturing Messaging Specification. That's what's used in Europe. US doesn't like MMS that much. They like DNP3. Okay, we'll map it to there. So what I'm showing here, it's sort of a roundabout way of getting here, is that these are some of the key standards that are used in the utility industry. Not all of them, but they're certainly some of the key standards. And what I'm trying to do here is show them at the different levels, at the different what are called GWAC stack, grid-wise architecture levels. I could do a whole session on this, but I think we're closing in on the end of the session here. So these are the core smart grid standards for utilities. There's another set here that are for the customer-focused grids. So you have BACnet, you have ANSI C12 for metering, you have the NESB, some of the NESB things, SEP, and so forth. So this, I think, is a good overview of what was sort of available to us for DER and why we ended up selecting the ones that we did. And this also shows sometimes the question has come, why didn't we use the Common Information Model, the CIM? And the basic reason is, as you can see first here in this diagram, 61850 is focused on field equipment, as I said. And it has many different domains, including the substations, DER, distribution automation, the customer site, and so forth, generation, got hydro plants. The CIM is much more focused on the control center, sort of application-to-application interactions. It means it's not really set up to deal with equipment that's got its own little idiosyncrasies. That's just not what it's there for. It's there for a different purpose. So what we spend an awful lot of effort trying to do is to figure out exactly how these are all going to mesh together. That's called harmonization of 61850 and CIM, and it's an ongoing struggle. I will go no further than that. This is just a very brief overview of 61850, where you have at the very top, these are the nouns, these are the objects. At the very top, you have logical devices, like, say, a photovoltaic system. Then under that, you have logical nodes. One may be for the panels, another for the inverter, another for the control system, another for a tracker if it's one of those tracking ones. So there are different logical nodes all under that. Then you have the data objects themselves, and this is, what the voltage is and what the temperature is of the day and where the, all of this sort of stuff. And then you have common data classes, which are basically the format, so that there's a well-established format. so that if one system is talking to another system and it sees, this data object, it knows precisely what's in there, so that there doesn't have to be additional playing around, at least conceptually. There are always little twinges there. And then we have common attributes, I won't go into that, and standard data types, floating point, integer, standard sort of stuff. So those are the nouns. And then we also have abstract services, which allow you to do things like report by exception. In other words, don't tell me anything unless you have something important to tell me. I don't want to hear, every 10 seconds this. I want to know it only if it's that. So there's a lot of these services that are, again, mapped. And just one final slide, a tiny bit of cybersecurity. It's an eye chart, so I won't go through it, but if you're interested, this is how the cybersecurity for DER is beginning to come together. And so we're just identifying some of the standards here. This is associated with 61850, and some of the IEC cybersecurity standards. Again, I could do a whole session on this. This is a one-slide presentation, so of this. So I'll leave it at that. So
you'll make it available to us.
Yes. So now it's question time, or is it too late for questions?
No.
Or you want?
So we have a microphone that we can go around and ask people to speak into it. And then what we'll do is we'll repeat the question here for the sake of the webinar folks, because even though there is amplification of the sound, it doesn't make it through the speaker phone. So if there are questions, here's a question from Mike Shea.
Thank you for the great talk. Question here is, I see all these things still basically utility-dominant world. So what these other companies like IBM, Cisco, Google, maybe even one day Facebook, because they own almost over 900 million of worldwide citizens.
Yeah. So the question basically is, what other companies, this seems to be somewhat utility-focused, what other companies are involved, like IBM and Google and maybe even Facebook? And to me, the answer is the utilities, first of all, have to be involved because this happens to relate to electricity. But from the customer perspective, Google, Power Meter, a bunch of others, Cisco, of course, has its routers, and they're going to be tremendously important for the communications and the cybersecurity. So there are a lot of players getting involved. There's a company called eMerge that's dealing with a DC, just strictly DC networks. Okay, well, that's a whole new concept. Now, of course, that's electrical, but it's not utility particularly. And as I mentioned before, the electric vehicles and so forth. There's the number of players, the number of stakeholders in this effort of DER is enormous. So it's a challenge, and there are many, many players involved. In this effort, this functional effort, we had over 100 people on weekly calls, just discussing some of these issues. Well, not everyone was on the call every time, but, there were at least 100 people, and then there were sort of 500 sitting on the sideline listening to the details.
You have a question? Oh, yeah. Could shrink the...
Oh, okay.
There may be some questions.
Okay.
We have a question from Green Tech Media.
Okay. Can you give examples, citations of projects that are combining all the levels of the DER to utility ISO management that you described? I would say that at this point in time, that is a vision of the future. Nonetheless, in California, I think that there's a lot of pressure on to start really building this. So the utilities here in California are on the hook to deal with some of this. The California ISO is very interested in the outcome of this, but in reality, it's still very piecemeal. And this is baby steps. You have to start with what you can do and build up. So it's important to have a vision. It's important to know where you want to get, but you're not going to implement it all right away.
Let me just make a technical comment here. Some of you are having intermittent problems with the internet on the audio. In those situations, the best thing to do is to just dial in to the phone number 650-479-3208, and then there's an access code. Your screen has that when you logged into the WebEx. Just use that access code and come in, and then you can hear the audio clearly if the internet is not working for you. We have a question here in the audience.
Yes. Hi, Francis. Thank you for sharing your outstanding knowledge with all of us. We appreciate it. My name is Rose Gabriel with Sustainable Silicon Valley. And my question to you is, what are your predictions for the milestones that will happen in this whole complex smart grid arena that we're talking about here today? What breakthrough technologies do you see are already here or are coming or are needed? So what are your predictions, and when, if you can?
Well, my predictions, the question was basically what are the milestones and what are my predictions for what the milestones might be in getting this vision of DER systems in there. And I will again say it's going to be piecemeal. And I think there's nothing wrong. In fact, I think the best way is to start off small, maybe have a community. Marin County is a good example. Small group that does their thing, knowing that later on they might get interact more with others. And then there's another project over here. The utilities do this over here. Somebody develops software that can better manage the inverters, or they can build software that'll do, say, contingency analysis or volt var optimization and all of these things that utilities need. And of course, there's the whole customer side where at the moment it is still not 100% cost effective, certainly to actually install some of these DER systems unless you have some additional advantage, like, support from the state and things like that. So I don't see that there's any major, today, yesterday it was like this and today now we're home free. I think it's going to be a lot of piecemeal actions. And if people have a similar vision of where ultimately they want to be and make sure that their systems can be added onto or modified to make sure that that vision can be added later on, that's what's going to make it work. But we've got to have that overarching view, because otherwise it'll be all over the place. It'll just be a disaster.
There is a question online after this one from...
Okay. Okay. Where are we seeing the most need for managing all of these disparate DER systems? Perhaps California utilities trying to manage heavy penetrations in distribution substation feeder level? How does where the problem is emerging first dictate how the DER management systems are being put together in their first real-world versions? Yeah, I think this is again one of the issues where if we have a good enough vision of where we want to be, then we really have to work towards it. And as I said, we've got now these functions that are defined for certain types of DER systems, pretty much for most of them, but most of them have not been actually implemented. I know a number of the inverter manufacturers are actually putting in a lot of these functions. Whether they first go into a substation or whether they first go into a residence or into a university campus, I think the answer is we really need to have lots of different people doing different pieces of it. There's no one single place to do this. It's not a monolith. It is by its nature distributed, and that's why it's, a challenge.
Yeah. I'd like to make a comment here about distributed energy resources. A lot of people will argue against distributed energy resources as if there's this amazing alternative available. And the sad part of it is there isn't. And the reason why there isn't is because we have spent a lot of time away from doing the research and development necessary for the next, what you'd call the ultimate source of energy. It just isn't there. So if you think of it like a linear programming problem, and you start putting all the constraint lines that are coming from the Sierra clubs and from the public utility commissions and from customer engagement and all of these things, and then you look at what is available. I mean, do we want to just continue putting out peaker units and dependent on natural gas that we dig deeper and deeper into the ground to get? And when are we going to include the cost, the risk associated, the environmental risk associated with that? Not even talking about the heavy metals that we're going to bring out from the inside of the earth and spread them out without any NRC regulation. So it's not like a luxury that DER is. DER is today something we need to talk about. Tomorrow will become a necessity. So there's an easy way of doing it and a hard way. The easy way is, just like sit now and as you're looking at use cases, do the analysis, come up with the requirements, communicate that to the vendor community so that there are proper roadmaps for products in this space, as well as the standards for interoperability, making sure that there's a good SCADA system there that can manage the field equipment Francis was talking about, have a good mapping with the common information model so that the data goes back to the enterprise and the proper reporting and tracking is occurring so that there is good investment in this space. That's the easy way. The hard way is the ostrich method, where literally every customer who thinks they have a DR system puts their head into the ground like an ostrich and creates their own little island on this side of the meter. And then what's going to happen is all these distribution companies are going to have very few kilowatt hours that they'll have to deliver at specific times that they absolutely have to do because DER is not delivering at that time. And guess what? All that investment cost has to be amortized over those few kilowatt hours. Are you willing to pay those huge surcharges on your bills for that fixed cost from the distribution company because DER has created a bunch of net zero sum games? So
I'm one of them.
We absolutely have to, and this is why I'm glad that Craig Lewis and the Clean Coalition is here, because this is what it's all about. We have to create a good wholesale market for this, and we've got to make DER affordable, not just for people who can buy technologies and stick them on their roofs, but for everyone, so that clean energy is a real option. And we'll take some more questions. And then what we're doing after this is we're going to have a networking break, and then we're going to have a panel discussion. So during the break, we're going to terminate the recording because we don't want to have blank snowflakes and things like that in our recording. And then when we come back, we'll start a new recording session. And Ed Cazalet has some slides he'll share. And then, Craig, do you have any slides, or are you just going to speak off the cuff?
I didn't bring any slides.
Okay. So we're going to rely on your Toastmaster capabilities today. Okay, very good. So we'll take a couple more questions, and then we should take the break, because I know people are getting a little uneasy.
I have the microphone, so I guess I get privilege. Realistically speaking, Facebook is already public, so they got a big wad of cash called other people's money, right? So hypothetically thinking that they could turn the entire menopause campus as a microgrid microgrid and also putting tremendous amount of DER, just like Erfan described it, and saying, okay, East Palo Alto, I mean, you're kind of economically disadvantaged. I'll just power you as a community for free. So what's technical challenges they have to go through in case Facebook CEO decided to do this kind of charity work?
Okay, so the question was, if Facebook, who happens to now have lots of spare cash, well, we think they do, if they decided to, say, invest in East Palo Alto and put in DER systems for everybody there, what would the technical challenges be? And I would put them on, first of all, just physically getting, say, all of the PV systems in there. But now we would have only generation. So you'd probably want to put some storage in there as well. And you'd want to be able to balance that. So you would have to have those DER management systems like in the blue box. And you could put a few of those around. You would kind of treat it like a community. And you could put that in there, and it would manage sort of locally the generation and the storage. But this also means you need to put in communications. And one of the challenges is the cybersecurity aspect of this. You can't get away from it, even though, people tend to have their eyes glaze over when you say cybersecurity. But you take a look at East Palo Alto, these DER devices are now going to be in private homes, in buildings that are not really known for their physical security. They can be, the systems can be stolen. They can be destroyed. They can be hacked. So we need physical security as well as cyber security to make these things work. And then, of course, let's assume there's enough Facebook money to take care of at least a lot of that. You're never 100% secure. Then you will have to have PG&E in that case. Really, unless Palo Alto wants to get into this, the utility, Palo Alto utility, one needs to then manage these DERs. They have to have that complex applications in order to know what to do if there's this high penetration all in one place. It then becomes, Peter and Paul kind of fighting over each other. So there would be a lot of challenges, but I think what it would be is a microcosm of all the kinds of challenges I've been talking about. So it would be a very interesting experiment.
Let us go to the questions on the webinar, and then we'll come back to the audience. So there are a couple more questions.
Okay.
I see the scroll bar moving.
Yeah. Okay.
I think there was a question above that, too.
I'd gotten that one. Oh, no, I hadn't seen that one. Okay.
Yeah, there are a whole bunch of St. John questions.
Yeah. All right, so let's see. Okay, wow.
This is media,
Yeah, there's a lot of questions here. I hadn't realized. Okay, so how do we stay abreast of changes and updates to IEC 61850? Or how can we get involved in helping shape changes moving forward? Oh, that's near and dear to my heart. I spend a lot of time working with the 61850 and putting in updates and changes to it. I think there are a number of ways to get actively involved. One of them is to participate in the EPRI project that's still ongoing, where we're defining new functions. Right now we're working on microgrids. We have not yet developed the object models for these microgrid activities. So that's one direct way. Another way is in the SGIP, we have what's called the DRGS DOOG, which stands for Distributed Renewable Generation and Storage Domain Expert Working Group. I have to stop and think about all of those acronyms, horrible things. Anyway, we do have a couple of groups. One is being led, well, Wendy was sort of leading it, that's directly working on some of the object models. I'm sort of leading the group that's looking at use cases and information flows and object models. We have meetings every other Monday. There was a meeting this Monday, so it'd be 2 weeks from now there'd be another meeting. And some of the actually some of these diagrams that you just saw, I presented to that group this morning. So, and what we would be doing there is getting the use cases and therefore sort of building up the need for particular types of information flows, which would then lead into object models. If you really want to get involved, join the IEC TC57 Working Group 17. And we always need good, dedicated people to help us out on that. And there we get into the nitty-gritty of exactly how to do the communication modeling.
So, go ahead, Matt.
Hello, am I on? How do I?
Are they rechargeable?
Oh,
well,
actually,
come up here, Wendy.
We have a lavalier one too.
This is an incredible opportunity I want to add on to this, so if you don't mind.
Yeah, you can just speak.
I'm Wendy Almstad, and I work at the California Public Utilities Commission. I'm an electrical engineer there, and I have somehow convinced my commission to let me work the last 2.5 years in the smart grid interoperability work that's been going on. So what I wanted to do was plug, for me, I think if you are interested in high level, and in high level we need a lot of technical people involved right now in the high level requirements, but even connecting the low level requirements to the high level requirements, if you're interested in doing that and help us really move things forward, the SGIP is, I think, a really important place to do that. I think also, like Francis said, this particular standards groups, really need people involved too. But the Distributed Renewables Generation and Storage Domain Expert Working Group, I'm very active in. Also, the Transmission and Distribution Domain Expert Working Group is another one, which we have virtual meetings, which to me is great. I have a 3-year-old. I can't travel right now. I mean, so I've been still very active in this 2.5 years. In the T&D Domain Expert Working Group, there's some work that was supported by NIST. Hopefully it's going to continue to be supported because I think it's really critical by Noam Markushevich, which is on a transmission bus load model, which it kind of doesn't really describe what it really is about, which is it's actually aggregating dynamic, near real-time distribution operations data, presenting that to the transmission system in a transmission bus, being able to accept commands from the transmission system or requests or whatever, and then send to the transmission system what's really going on in the distribution system, but not all in every point, just some general, hey, this is what's happening in your transmission, in your distribution system, every 5 minutes, every 10 minutes, every 15 minutes, whatever. The more you feed into it, the more accurate it's going to be. But that's some really important work that's happening. So what this ties into is that in the technical area, we are starting to see that the technical solutions are definitely, I would say, bringing up the regulatory market issue, jurisdictional issue. They're not fitting into the existing schemes that we have now. So we have, under the DRGS, the Distributed Renewables Generation and Storage working group, we have 5 subgroups, and Francis was starting to talk about those. One's a standards group, one's a use cases information exchange group. Another one is a microgrid and hierarchical control. So how can we do these DC microgrids and other kinds of microgrids, and then have islanded and then connect, have these hierarchical controls to the utility systems, hopefully. Another one is testing and compliance, but another one that's really, I think, very important, and we have a meeting tomorrow at 11 a.m. Pacific, and I really want to invite anybody, because I've been very active in this subgroup, getting it started, getting it going, and it's a regulatory and market issues subgroup of the DRGS. And there has a draft white paper that is available to the public online right now that we will be discussing and presenting tomorrow. We've been working on this for at least 6 months, and we want to present it to people and get their ideas, want to make this open. And what we're trying to do is just describe the issues and the technical issues and the regulatory jurisdictional issues. People are not going to go forward with these DRR solutions if they're not getting adequately compensated for it. That's a big problem in the way things are now. And so I just want to encourage anybody, if you're interested, definitely talk to me. 11 o'clock tomorrow. It's a 1-hour meeting. I think it's going to be a very important meeting. There's been a lot of work coming to date up to this meeting, and then there's a lot of other things. So I'm Wendy Almstad, CPUC. Just wanted to add that plug. Thanks.
All right. Very good. So I'm going to exercise my authority as the host now to start the networking break now, and then all questions in the audience and on the internet we're going to accommodate in the panel discussion, because I really want us to spend that hour in a panel discussion. So we are getting close to 5:30. We're going to start the panel discussion a few minutes after 6, like 5 minutes after 6, so we have a good solid 30 minutes. Now what I want you all to do is spend about 5 minutes networking here before we invite you into the break room, because Chris and I are going to go and lay out all the goodies for you over there. So I want you to stay in this room for about 5 minutes or so, and then we'll come and we'll get you. So I'm telling this so that the webinar folks are all salivating knowing that refreshments are coming. And I'm now going to end this recording, and then we are going to start a new recording after the panel discussion starts.